All right. Good afternoon, everyone. How are you guys doing? How was your weekend? All right. Okay, good. You ready for the more geomechanics? Remember, we have 10 more days before the first midterm, right? So Wednesday, not this week, but next week, that's going to be our midterm. And on Wednesday or before, if I have some time this afternoon, I'll be uploading some practice exams. So there you will have a fair idea about what to expect. The exam is going to be very similar to that, same format, same number of questions, but of course the questions are going to be a little bit different. And that's going to help you in order to prepare for the exam. And I'm going to upload also probably the previous year exam too, so you have more problems to work with. But remember, I'm not going to take anything that we haven't seen. Probably I might just change the script a little bit. But if you have done your homework, and if you know what you're doing, if you understand what you're doing, that should be enough. Okay. So let's see. So far, we have learned about stresses, that we have 3 different stresses in the subsurface. We learned about the stress tensor and how it is related to strain. And that link, we did it through, so far, through the theory of elasticity. And we have solved a few simple problems of elasticity. For example, let me find it. And let me initiate the dog camera. The first problem that we solved was about a uniaxial strain stress path. And that's the strain path, this one, that applies to many places like this one without any tectonic strain. Without any tectonic strain, using the theory of elasticity and linking stress to strain, we were able to find the equations that tell us what is the horizontal stress. And we went a little bit further, and for example, for this other case where we had tectonic strains, we found the equation of stresses as a function of strains and vertical stress. Okay, but this problem was very simple. Now what I'd like to talk about is a general solution for a problem of geomechanics in 3 dimensions. And for that solution, we're going to need something more powerful in order to solve the equations of elasticity. So, for example, if you wanted to solve a problem of multiple hydraulic fractures out of a single wellbore, then one equation is not going to be enough, or the solutions that we have seen so far, they're not going to be enough. So let me finish writing this. So we were saying, what about if we had a medium in which you have a horizontal wellbore, and out of that horizontal wellbore you have multiple hydraulic fractures? What about if those hydraulic fractures were not to be planar? If one would be shorter than the other, or if sometimes, because you may have a fault, which is a weak discontinuity in the rock mass, probably you have a fracture that starts propagating in one direction and then picks up the fault. And in addition to that, we have stresses in horizontal direction, you have stresses in vertical direction, and let's say that the bottom is not moving. And I give you all of this, and then I tell you that I want to know what is the stress in a place like somewhere over here after you do the fracturing. Or I want you to predict what is going to be the shape of the fractures based on the initial state of stress. Do you think you're ready to do that with what we have seen so far? So probably you're not right now, but you have seen the theory already. And it's just taking the theory into something a little bit more complex like this. And actually, it's not too difficult. But you have already seen the theory, and now we will see how we extend that theory, but we're not going to solve these problems, because for some of these, you may need to do in a computer. For example, in your reservoir simulation class, you're coding your own simulation, right? You're doing that for single phase fluid flow. I think in Reservoir 3 you do that. But that's, you didn't have that yet?
I mean, we're taking it, but we haven't started that.
Okay. So what you're going to do in Reservoir 3 is to code your own simulator in order to better understand how a simulator works. But this is not other thing than solving an equation. And for example, I want to make this analogy with reservoir simulation, because you are going to do this at some point. Probably the parts of mechanics, you will not do it, but you need to understand what's inside. And we have already seen quite a bit of the theory that is going to allow you to do that. But let me go through this very quickly. What is Darcy? What's the equation for Darcy? Say again? Q? K over mu, yeah. K over mu, delta P over delta X. But what about in 3 dimensions? I'm talking about direction in flow in 3 directions, in a 3-dimensional space. Remember that we always have here a 3-dimensional space. So if you want to extend Darcy to 3 dimensions, you need to extend the gradient to 3 directions. For example, the variation of pressure in direction 1, variation of pressure in direction 2, variation of pressure in direction 3. And since you have 3 different types of variations, here you're going to have the flow in direction 1, the flow in direction 2, and the flow in direction 3. And those 3, they add up and they make a vector in 3 dimensions. So for example, here I could have fluid that goes into this direction, and that's going to be a vector. Okay, that's Darcy. And what about mass conservation? Anyone remembers that equation?
Mass in minus mass out equals.
Okay, yes. And that, you write it like this. The variations of fluids in direction 1 plus the variation of fluids in direction 2 plus the variation of fluid in direction 3, that's equal to 0. So what that means is exactly what you said before, but in 3 dimensions. It means that what gets in one direction, it has to get out in some other direction. So for example, if 1 comes in this direction, then what has to come out from there is also 1. So under state conditions, this is the equation of mass conservation, and it means the differences of fluid in direction 1 plus the difference in fluid in direction 2 plus the fluid in difference in direction 3 all has to be equal to 0. There might be some positive terms, there might be some negative terms, but then you add them all up, and that's going to be 0. Yes?
Why did you include the dq over dt term?
The what?
The change of time. Why did it?
Oh, because I'm assuming under steady state conditions, because I want to make this equation real simple. Under state conditions, then we don't consider time because it's steady state, and we just oh, I didn't want to do that. We just equal all of that to 0. So, okay, we're very close to what I want to get. All right, so if you combine these two equations, we know what is Q1, right? Q1 is in the previous equation. Q1 is dp dx1 times this. And Q2 inside here is dp dx2, and the same for Q3. So if I put equation 1 into equation 2, what I get, this is going to be a common factor everywhere, and so I'm not going to write it because it's going to be everywhere equal to 0. Okay, well, I can write it. It's going to be just a common factor. And now, since I already have a derivative, this is going to be the second derivative of p in direction 1, second derivative of p in direction 2, second derivative of p in direction 3, and all of that is going to be equal to 0, and this is going to be 2 times. And you're going to solve this equation in Reservoir 3, and you're going to also add the part of multi-phase fluid flow and also unsteady state conditions. But at the end of the day, all I want to tell you is that this is just a differential equation. And if you solve this differential equation, you can tell in which direction the fluid flow is going, and you can calculate flow rates, you can calculate gradients of pressure with different boundary conditions, but it's just a differential equation. What is the unknown in this differential equation? What is what you solve for? So, for example, you may have a problem of fluid in a wellbore over here. You set a constant pressure, bottom hole pressure. You know here the far field pressure. What do you solve for inside the domain? You solve for pressure. P inside the equation is what you don't know. You know that at the beginning, you know that at the boundaries, but you don't know that everywhere, and you don't know that at all times. So your unknown is pressure. Let me delete that so it doesn't look like a vector. Okay, so this is what the reservoir simulator does. And you're going to see a lot of this. Now let's come back to mechanics. In mechanics, you can do something very similar to what we just did. But what you use instead of Darcy, that is going to be changed by the constitutive equation. Notice that Darcy tells you about the property of the rock because you have permeability, and also a property of the fluid because you have viscosity. Well, in mechanics, the properties of the rock are going to come from the equation, for example, that tells you what is sigma as a function of strain. Also, conservation is going to to be not conservation of mass, but conservation of momentum. And conservation of momentum is basically equilibrium. I'm not going to write it here because that's a long equation, but that's basically equilibrium. And there is one more equation that we need in mechanics, which is something called the kinematic equations. And we also saw that. Kinematic equations that tell you what are strains as a function of displacements. Strain as a function of displacements. And equilibrium tells you what is the variation of sigma in space. It's actually a little bit more complex, so just let me write. Sigma as a function of space. Okay, so very similar to what we did here, but it's going to take us probably 20 minutes to do everything for mechanics, similar to what we did for fluid flow. But you can write a similar equation to this one, and it's going to look like this. Don't be scared by the inverted triangles, okay? I'm going to tell you what they are in a minute. Okay, almost done. That's our final differential equation for mechanics, similar to the one of fluid flow, where I want you to notice a few things. You don't have to remember this, but the only thing that you have to remember here is that there is an equation, a differential equation, similar than for pressure for mechanics, where now your unknown is the displacement, so you solve for the displacement. And look over here. In this problem, it doesn't matter, but if we put it as a function of time, it would matter what k is. You have some parameters or like G. What is G? It's a shear modulus. And lambda is another type of elastic modulus, which is a function of Poisson ratio and Young modulus. If I remember correctly, it's written like this. Let me check. Yes, that's correct. So lambda and G are just parameters that depend on the elastic moduli. And B, if this is a body force, for example, gravity, and the only thing left that we need to explain is what these triangles are. Anyone knows what these triangles are? Gradients, derivatives, but they are just derivatives. It depends how you combine them. For example, this is a second derivative similar to that one. This one is it's like a dot product between the derivatives and the vector, and then you take divergence of that. Don't worry about that, okay? You don't have to remember that. You just need to know that this is a differential equation, that here you have derivatives very similar to the ones over there as a function of space. For example, that guy over there is a vector. but it's just a derivative in space. And when you solve these equations, when you solve for these displacements, then if you know the displacements, you're going to get to know the strains. If you know the strains, you'll get to know the stresses. And with these equations, if you solve them numerically, you're going to be able to solve a problem like this and to tell what the stress is, what displacement is, what the strain is in a complex problem like this one. So I was looking before for a few images to show examples of that. These are the equations that you need in any hydraulic fracture simulator. Hydraulic fracture simulators, they utilize these equations to tell you, for example, what is let me see if I can see the image. No. Okay. All right, this is what I wanted to do. If you want to predict the thickness of a hydraulic fracture, it will depend on the properties of the formation, like the elastic modulus. The stiffer the rock, the narrower the fracture is going to be. The shape is going to depend on the different layers that are in that formation. If you want to predict how multiple fractures open up, and let me see if I can. Okay, this is a good one. If you want to predict what is the width, again, of multiple fractures, you need to solve for these equations. And the same way that you solve for pressure in a reservoir simulator, you can solve for displacement and stresses in a mechanics problem. Every single hydraulic fracture simulator has these equations in it. Probably you cannot see it, but they are there. And you solve for them when you solve these type of problems. But we're not going to solve them, okay? But you need to know that this equation exists, and if you want it, you could solve it. If you stay in grad school and you want to take my advanced geomechanics class, then we're going to solve them there. But not right now. Okay, so then let's summarize what I say and add a few more things. So the solution for this mechanics problem, we're going to have numerical solutions, the same as what you have for the reservoir simulator. And also, for example, for the problem of a single wellbore, you have analytical solutions, right? In mechanics also we have analytical solutions. When the problem is relatively simple, we can solve that differential equation directly. And here, when we go into wellbore stability, we'll talk about the Kirsch equations. When we talk about fractures, we'll talk about the Griffith solution for a fracture. And for the numerical, we'll not do this, but when we get later on to solve some problems in of depletion, hopefully we'll get to there. You can solve this with a method which is called finite differences. And CMG, this is reservoir simulator that you have license to here in the department. Very good reservoir simulator. Also has a module for geomechanics, and it's solved with a method called finite differences. Otherwise, there are many other simulators that use what is called the finite element method. And that allows you to solve for problems of mechanics in 3 dimensions. So Okay. So we'll see this later on. We'll see this later on. I hope that we'll get to see that one too. All right. But for now, this is everything I wanted to talk about a general problem of elasticity. Remember, those equations are there, and you can find them also in reservoir simulators. Okay. Any question so far? No? Everything is good? Okay. So let's move to the last topic before we go into the failure of rocks. And it's something that I call real rocks. Because so far we have dealt with problems of mechanics in which the rock was isotropic and it was just linear elastic. And real rocks are not like that. First of all, real rocks are anisotropic. What does it mean, anisotropic? And I talk especially about the mechanical properties. So something isotropic is something which is the same in all directions. Something anisotropic is something which is not the same in all directions. And rocks, especially sedimentary rocks, the ones that we are mostly interested in, are very anisotropic because of the natural sequencing and layering of rocks as they form, of sedimentary rocks. Because of that, usually, if you take a sample in horizontal direction and you load it into in a load frame in order to measure its Young modulus, you will see that the properties are going to depend on if you take this sample horizontal or if you take it vertical. Which one you think is going to be softer, the vertical or the horizontal? Any suggestion? I'm going to give extra points to anyone that gives me a good idea why that could be like that.
Harder in the vertical is more compacted.
No. Yes.
I think it's softer in the vertical because of it means the same volume is more compressed in horizontal because of the gravity of the convection.
Okay, you're getting close, but no. Any other suggestion? Let me improve here my shading the layers. It doesn't look very good in the. Okay, let me give you a hint. What about if I told you that these dark layers are soft and the light layers are stiff? Imagine like the light layers is a carbonate, very stiff, and the dark layers are a shale, which is relatively soft. In which direction is the rock going to be softer?
Softer vertically because
Why?
the white section, which is that horizontal,
Yeah.
that's mostly the stiff rock. But vertically, you would have to pretty much like sum up like a weighted average of the thicknesses, and that will like get you a stiffness that's lower.
Okay, but give me an easier explanation of that.
So vertically, you'll have a greater composition of the soft rock. horizontally though.
Oh, but I mean, I could take these rocks in a way that I take the same amount of each.
It's going to be softer vertically.
Okay.
Wait. Yeah. Yeah, it's going to be softer vertically because you're pushing against both. But when it's horizontally, like you have an entire column with a stiff rock,
Yeah.
you have to push against it all the way.
Okay. Yeah. I think there you're getting closer to the answer. So imagine, in order to make it simple here, imagine I could pull up a picture of it, but I'm going to draw it here so you remember. Imagine a marshmallow or imagine an Oreo cookie, and you are pushing vertically the Oreo cookie. Since you have a softer material inside, this is the cookie, okay? And it's going to be just easier to press the softer part in a direction, a preferential direction, where you have the soft layers. So the rock is going to be the same, and the horizontal Young modulus is going to be higher in the, this looks misleading, just let me do it the same length. The Young modulus is going to be higher in the horizontal direction than in the vertical direction. Because if you have soft layers in the vertical direction, then it's just going to be easier to push this in this direction than to push all the stiff layers in this direction. So when you press this, or you compact it, or strain it in this direction, you have to push all the stiff layers. You have to deform in the same amount as the soft layers. While if you do in vertical direction, you can deform a little bit the stiff layers, and you can deform a lot the vertical layers. So in general, let me summarize this. Real rocks are anisotropic, and they are stiffer in horizontal direction than in vertical direction. There are some exceptions to this, and the exception is when the rock is fractured. When you have vertical fractures, then the rock may be softer in the horizontal direction. But rocks tend to be very anisotropic. And I need to get an example from my lab, but I don't have an example here of a shale. But it's very obvious sometimes that anisotropy. Okay, that's the first thing. Second thing, rocks tend to be also not only elastic, but tend to be elasto-plastic. And what that means is that they will deform with a combination of recoverable and irrecoverable deformation. We haven't talked about the irrecoverable deformation yet, but that's always going to be there. The same kind of experiment, and this is something that you have seen in some of the material I gave you, but I didn't explain that yet. I do a uniaxial stress loading experiment. You load it, you get to a point, and then we wait, unload it, and then load it again. Let me make this a little bit better. Load it again, and then break it. When you do this type of loading, first of all, there is what we call over here in this region, the loading modulus, and in this other region, we'll have the unloading modulus. And the unloading modulus, let me zoom in a little bit. The unloading modulus is going to be larger than the loading modulus. And the reason for that is when we do this type of deformation, we get all of these irrecoverable strain. The loading modulus has both, has recoverable and irrecoverable strain, and the unloading modulus just has the recoverable strain part. And because when we measure the loading modulus, we have both, the material tends to look softer. But the problem is that actually you are producing some strains that are not recoverable, and that's why it looks softer. And if you treat it as a black box, then it will be softer. But that's because it combines both the irrecoverable and the recoverable strain. If I were to, for example, now to unload this rock also in this direction, I will have all of this irrecoverable strain. So that's why in the data that we that you did for homework number 2 or number 3, I don't remember now, you had these cycles of loading and unloading because we wanted to compare those two. The question now is which one you use in practice. If you were to do, for example, a hydraulic fracture design, which modulus would you use? The loading modulus that puts together recoverable and irrecoverable strain, or the unloading modulus?
Unloading, because it determines if the fracture stay open or not.
The unloading, you said?
Yeah.
Uh,
Because I think like once you deform it, then that will determine whether or not it closes back in, or how much it closes back in or not.
okay, that's a good point. But when you make a fracture, you're actually loading the rock because you're opening a fracture. Then if it closes or not, probably when it closes back, you could use the unloading. But when you make a fracture, it opens up and you're actually loading the rock. So in that case, you will tend to use the loading modulus. Or for example, when you're doing computing compressibility of the rock, and you need to know the compressibility of the rock, if you're doing a loading process by loading the rock, by lowering the bottom hole pressure, then also that will be a loading process. If you're doing injection of a fluid for getting rid of water, for example, and you pressurize the reservoir, that will be an unloading process. So it will depend on the process. For loading processes, you will tend to use a loading modulus. For an unloading process, you will tend to use an unloading modulus. Okay, so we're going to get back to this plasticity part later on, but for now, remember that all rocks, even if you think that they are fully elastic, they are not. They always have some component of plasticity. And the last one is visco-elastic behavior. And visco-elastic, that means that there is going to be a part of the deformation which is time dependent. And there are going to be, I'm going to summarize a bit here, 3 types of phenomena that are going to tell us if a material is viscoelastic. The first one is going to be looking at the Young modulus, and it's related to the previous experiment that we did before. So I get a plug of rock, I load it axially. What do you think is going to be stiffer? If I load it very quickly or if I load it during a long time? So is the rock going to be stiffer if you load it quickly or if you load it slowly? No. So it's going to be stiffer if you load it very quickly. When you load the rock very quickly, the same rock is going to look stiffer than if you do it slow. For example, you may have the same rock and it will give you completely different Young moduli, either if you do it in the laboratory in the term of 1 minute or a few minutes. If you do it, for example, in the field in 10 years, for example, during depletion, or if you do it over geological scale in 1 million years. In 1 million years, the rock is going to look a lot softer than if you do it in 1 minute. And that's because you let the rock flow and reaccommodate in time so that it can deform more easily. That's why when you have faults and faults, rocks can fold and form anticlines over a long time because they tend to be a lot softer over a long time. And this is very important, especially when we compare laboratory tests with field tests or with processes in the field, because those time scales are going to be quite different and the Young moduli are going to be different too. Okay. And this is something which is called, the variable here is the change of strain with time, and is strain rate. The higher the strain rate, the stiffer the rock. This is number 1. Number 2, let's say that I get a rock, I load it with a low frame, and then I maintain that load constant with time. I'm going to plot here strain. When I load it, say if I compress it, the rock is going to get smaller and it will show some strain. What is going to happen after this? Will the rock keep the same strain or will it deform more? What do you think? Why? And how is that strain called? Anyone knows the name of that? This is called, is going to tend to an asymptotic value, and it has a particular name. It's called creep. Creep strain. And rocks that creep a lot are creepy rocks. Like, for example, salt rocks. Salt rocks tend to be quite creepy. Soft mud rocks tend to creep a lot too. And these are the type of rocks that we were saying before. If you let them enough time, if you put a vertical stress, the horizontal stress is going to tend to equal the vertical stress. I'll try to come back to this example in a bit. But let me finish with these three types of phenomena. Okay, this is called creep, and it's very important. Talking about an example, real example, about hydraulic fracturing. You can open a fracture. You can prop it. But over time, the rock is going to slowly creep, and it's going to close. And some of those fractures that were originally open, they may close. Sometimes the formation may be so large that if you have propant, it's going to get inside the rock. It's going to get embedded. And your propant will not prop the fracture anymore. And this is due to the creep strains. All right. Number 3. I'm going to do the opposite test now. And we did this actually here in the laboratory in our low frame. I'm going to deform the rock. And after I deform it, I'll keep that length constant, or that strain constant. The question is, what is going to happen with stress? Well, I know if I compress it, stress is going to go up. But my question is, what happens after that point? If I keep it constant, what do you think would happen with stress in a viscoelastic rock? A viscoelastic rock doesn't like stresses, tends to deform in order to accommodate stresses. So if you keep the strain constant, then the stress will go down and will relax. So these rocks that don't like stress, they relax. And that's called, is the opposite of creep strain, and it's called stress relaxation. And the same type of rocks, salt rocks, soft mud rocks, they will tend to exhibit quite a bit of stress relaxation with time. An example of this is you drill a wellbore. And well, it's actually an example for the previous one, but it's related to this one too. You drill a wellbore in a salt rock. If you don't case it fast enough, the wellbore is going to creep in and close back the wellbore. So where you had a wellbore, you may not have a wellbore anymore after some time. We have 1 minute, and I wanted I told you that I wanted to talk about this example, which is very important now. Remember that many times our objective in this class is going to be to get to know what is the horizontal stress. So just 1 minute, guys. If you have a constant vertical stress with time, a rock that exhibits viscoelastic behavior and under constrained conditions that cannot expand to the side is going to increasingly show bigger and bigger horizontal effective stress. And the bigger that horizontal stress, the bigger the pressure you're going to need in order to open a hydraulic fracture. All right, guys. That's it for today. I'll see you on Wednesday.